Hey everyone, I'm TJ. I'm a real-world Embraer 145 pilot and part of the beta test team here at X-Crafts. And one of the things we've been working really hard on towards the end of this year, getting this plane ready, is working on a lot of the system logic and a lot of the messages and system symbology in the cockpit. And we're really excited to show a lot of this off, so I've been charged with making a video that shows off a lot of the system stuff we've been working on. Alright, stepping on up into the front office here, first thing that you're going to notice is we have redone the layout, so we have a lot more paneling. The panel controls for the PFD and MFD are now present. New FMSs, these are the new Honeywell FMSs. We have a new Gust Lock, and we have a lot of new things that basically bring this aircraft's cockpit layout up to par with what you'd expect to see in any Embraer 145. So, as a 145 driver, I feel at home. All of these switches and knobs are in the same position, or as close as they can, with the different variations of cockpits going around in the fleet, to where I expect to see them, so that's really cool. And as we start to step through some of the systems, I'll show you some of the new cool things that we have simulated now. So let's go ahead and bring the aircraft to life here. We'll come up here and we'll go ahead and select the batteries. And you can hear them click on. And there's our oral warning test. The aircraft has come to life. And I want to show you the brand new EICAS that's simulated. As you see, it's first thing is that the font and layout is true to life on the Embraer 145. So we've gone ahead and really matched what you expect to see in the size, font, shape, and how things present. We've gone through the message list, the master message list that this aircraft, of all the messages this aircraft could throw, and we went through and identified the messages that are common, the ones that are not uncommon but not very common, and then the messages that are due to a system misconfiguration or a failure or things like that, and ranked the priority of each message. We've then gone through and with each message figured out what the conditions are to have that message come on, what makes them go away, how do we code it, and so on and so forth. So what we ended up with was a really, really good representation of messages you expect to see during flight. Any 145 driver that's with me right now knows when you turn this thing on, in fact you may even have more messages depending on the configuration of your aircraft and what equipment you have. But when you put this thing on, and right now we're just running off the battery, you can expect to see a lot of messages. The airplane thinks it's dying when it's at the gate. So we have a rudder system 1 and 2 inoperative, an aileron system 1 and 2 inoperative, hydraulic system 1 and 2 fail, and this is because the hydraulics are off, which we all know is pretty normal for sitting at the gate here, finding an airplane, but the airplane doesn't know that, so the airplane thinks it's dying. Same thing with engine 1 and 2 fuel low pressure. The engines are screaming at us saying, hey, I don't have any fuel being pumped to the engine right now, which we know is a normal thing. But of course the Embraer doesn't know that, so it presents all these messages, which is really cool to see all these simulated here. So now that we have the aircraft on batteries, let's get a power source to the aircraft. So I'm going to come over here. We would never really see engine covers on the airplane in day-to-day life, so we'll just pretend that wasn't on. Maybe maintenance was doing something and this plane sat here for a while. Let's go ahead and get a ground power unit hooked up to the aircraft. So I'll select that in the X-Crafts service window. And the ground power unit comes alive, or the ground power unit avail light comes on. So this is telling us right now that we have ground power available to the aircraft. Now, here's the fun little gotcha. I don't want to take this ground power until I know it's good ground power. So what I need to do is actually take a look at what the power being put out by the GPU is before I select it. To do that, we have 2 avionics buses on the aircraft, 1 and 2, and they enable all the other equipment in the cockpit. Right now, because we're running off batteries, I really don't want to spend a lot of time with those on because that's a great way to drain your batteries. But to check out whether we have enough power, or the GPU's putting out the correct power, let's go ahead and select avionics 2. And what avionics 2 does is you'll see is it selects the captain's MFD and the first officer's PFD. So both of those come to life. Our AHARS is still aligning. You can see AHARS 1 and 2 aligned. So we have an at fail and a heading fail. That's a normal indication right now. The plane doesn't know where it is, so it's aligning itself. And we'll go ahead and make this big. A cool new feature as well, just to show you, is that there's 2 ways to interact with these menus. The first is to use the display push buttons. However, true to life on the real 145, it's often awkward to get around the yoke when it's all the way forward in the Gust locked position. So what we've added, which is really cool, is you can also interact with everything here by simply expanding the menu and clicking on it. If there's something that requires a scroll wheel, like an altitude select or things like that, those are actually now available to be, you can scroll directly on this pop-out. Really, really cool feature. So we're going to come to our electrical page, the MFD status electrical page, and we can see a couple things. We can see the status of all of our generators, the status of our buses, status of our batteries, the temperatures. Batteries are ticking downhill here because we're sitting here yammering away without getting power on the airplane. And we can also see our ground power unit. It's plugged in, so watch what happens when you deselect the GPU. If I deselect the GPU goes away. The GPU will only show up on the MFD when it is connected. So that's true to life. It's connected, and we're showing 28.5 volts. 28.5 volts is an acceptable amount of GPU put out. If it's putting out more than 29 or less than 26, don't take that GPU. So we always check this. In Sim, obviously, it's going to put out 28.5, but you'd be surprised what you see on the line. So I'll go ahead. I like this. I'll take it. We select it. Power clicks to the GPU. And the batteries go amber. This is indicating that the batteries have been taken off the bus. Reason being, the electrical logic of the airplane does not want the batteries being charged by the GPU. It's not something that's allowed to be done. So it automatically clicks them off the bus to both preserve their voltage and so that the batteries are not connected to the GPU in any way. Now that we've done that, we can go ahead and select the other avionics. That'll bring on my primary flight display and the FO's MFD here. And we can see the aircraft is now fully powered. We see a couple things. First is I should be a little better about updating my nav data. Let's ignore that. You didn't see anything. And we can also take a look at the new FMSs. So if you've used the Citation 10, you'll be familiar with this FMS. It is the Honeywell series that comes with most Embraer 145s. Some operators, including mine, have universal FMSs, so I'll admit I'm not the best with this FMS, but it's really cool to see a custom FMS built for the aircraft. And we can go ahead and just get it loaded so that it'll pull up the main screen. Alright, so now that power is on the airplane, let's go ahead and first thing I'd like to show off are some of the system things that have been done to this aircraft. We'll step through the overhead here, and I just want to highlight a couple cool features and just kind of highlight some of the work being done on the systems. So we've talked a little bit about the electrical panel here. We've got the aircraft configured on GPU. We can see the electrical logic has pulled the batteries off the bus. The ground power unit, we talked about how it's the indication is that you'll see GPU avail whenever the power is connected, but until you select it, you won't see this white bar. Something important to know for people new to Embraer is that we have a dark cockpit philosophy. It's similar to an Airbus in the sense that when everything is normal for flight, so remember, normal for flight, if a panel is configured the way it should be according to the aircraft logic for a flight operations, you will see no lights. No stripes is what we call them. So, makes sense, right? Unless you're towing the GPU, and I sure hope you're not, you would not see a GPU stripe while you're in flight. This is only a ground item, otherwise known as non-normal for flight. In the same vein, we don't have the APU on, but for example, if I were to deselect the APU push button, the APU is a little bit of a different one. This button lives in the in position. Reason being is that the electrical logic is going to switch through generators, and any generator, APU gen or the 4 engine-driven generators. It's going to switch through these as required based on the situation. So taking the APU out of the mix, hard deselecting it from the EDL, the electrical distribution logic, is a non-normal thing. We're basically bypassing the automatic electrical control system. So we leave that in, giving it the ability for the computers to basically command whatever generator they want. Same thing with any engine-driven generator. We have 4, and no, this isn't a typo. Engine 1 and 3, or generators 1 and 3, are on engine 1. Generator 2 and 4 are on engine 2. Why? That's an Embraer thing, you'll have to ask them. But any single generator can be disconnected, but again, that's a non-normal. Another Embraerism is that we don't actually touch the generators, so unlike a 737, right, we're not switching generators as they come online. We leave these in and we let the computer take care of them. Another cool new feature is the essential power mode. So this aircraft obviously has 5 generators providing electrical power, 4 normally, but a 5th one is the APU. We have a lot of generator sources. It's very difficult to not have a generator. But if you were, for example, to have an electrical emergency where all generator sources are not available, you're in flight, and all of a sudden you have nothing providing power electrically to the airplane. You're on batteries only. Well, it's a very electrical airplane, and every single thing here is sucking power. You saw how fast our batteries came down while I was yammering away explaining some of the features when we didn't have a GPU plugged in. So the batteries will drain very quickly. So something you want to, if this were to happen to you, the aircraft is designed to put the airplane in essential power mode, which would power essentially the middle panel here. You would have your standby instrument, your radio management units on both sides, and you would have your EICAS. And that's what you get. PFDs go dead, FMSs go dead. You're in an electrical emergency, right? You're not flying an RNAV arrival. You're asking for emergency vectors to the nearest airport, maybe tuning up a VOR. Well, if this happens on its own, great. It puts the plane in a power saving mode, and that gives you about 40 minutes of battery life. However, if it doesn't go into that, say there's an electrical transfer failure, all of a sudden, every single thing on this airplane, all these avionics, every single thing, the lights in the cabin, the coffee maker, everything is now all of a sudden attached to your batteries. And your battery life may be as low as like 5 minutes. So a cool feature is this button here is designed if it doesn't transfer to essential power mode. It's guarded for a reason. We can select it. And you see that the aircraft is forced into electrical power mode. And look what came up. So because we've done this, we have killed everything except these emergency items. So this is booting up its own AHRS. We were still aligning. Now we have a no position because the AHRS doesn't know where it is. We have check PFD 1 and 2 telling us, hey, something's up with your PFD 1 and 2. Well, yeah, they're off the bus now. JipWiz is shedded. Let's see what else we got. Looks like, yeah, those are the new ones here. Basically, it's telling us here, hey, all this equipment starts screaming at you because it's off the bus. Well, yeah, there's a good reason. We've dropped down to emergency power. We can reset that here. And now our AHRS. The flashing messages are the newest. Our AHRS has started aligning once again. So, you know, obviously we're going to have to go through the whole alignment again because we've knocked the AHRS off the bus. Now we started it again. All right, stepping through here, we'll get the APU started in a little bit, but kind of stepping through some of the other electrical controls and what they do. I'll show the shed buses once we have the APU online. This aircraft is designed with a couple load shed buses that aren't directly related to emergency power. We have 2 shed buses. Some of the equipment that's on a shed bus, for example, is the nose taxi light, some of the cabin's MP3 player or music player, and other things that are considered essentially things that I wouldn't be upset about losing in if we happen to have a power loss, not a loss of all generators, but if, for example, we lost an engine, so now we only have half of our generators. I'll talk a little bit more about that because it has a special logic on how it works, but on ground power, the shed bus is fully energized. Once we start getting generators into the play, there's a little bit more coming onto that, so we'll come back to that. The bus ties controller is how we can interact with the electrical logic. There's a huge set of there's a whole pages and pages in the manual on different configurations of all the bus ties, depending on the type of electrical power available. It's all controlled by the computer, but we do have, and in certain failures, there are certain procedures that require you to hardwire things override, so basically all of the bus ties are energized, or turn them off. Again, this will be driven by a procedure when the electrical logic has failed. In normal operations, we never touch this, but it is there in case you need it. The AC power bus is off DC bus 1, so disabling that or enabling that. If you have equipment, different operators put different equipment on there. And my operator, for example, the printer and the JipWiz and the EICAS are on that bus, so disabling that would break your printer, for example. It just depends on how the aircraft's configured. We have a backup battery. What the backup battery does is it is actually the battery that powers the electrical control logic. So without needing these batteries, these power the airplane. That battery powers the electrical logic in an electrical emergency. We talked about our avionics push button, so remember that avionics 1 controls FMS1, or sorry, PFD1, FMS1, and MFD1, and avionics 2 does the opposite. Alright, so coming through some of our other panels here, I think we better get an APU online here, get some heat to the aircraft as we do this. As you've seen right now, we're sitting here in Portland, Maine, and it is -10 outside, so let's get some heat to the aircraft and we can watch how the APU comes to life. Embraer made our lives very easy. Embraer likes to use diagrams on the overhead, so if you ever have a question about what touches what, for example, what fuel tank does the APU feed from, well, it's all schematic here. APU comes off number 2. I can read, I promise. Right here, so if we want to turn on the APU, we got to give it a fuel source. Let's turn on pump number 2. And while we do that, let's bring up the fuel page. Now, this plane loves to beep at you anytime you do something. The reason it's beeping at us is because we had an engine 1 and 2 fuel low pressure, and now it's gone down to engine 1 fuel low pressure. So the logic goes, well, that's a new message. I don't really like that. So, of course, it's going to throw a new EICAS at you. It just gives you something to do. Okay, so we got the fuel page up. You can see, for example, the fuel page is looking at, we can show tank quantity, total quantity, the amount used, and the temperature of the fuel in the tank. So fuel tank temperature is another one that's monitored. If it ever gets below 5 degrees, you will get a fuel low temperature alert. Now, something that is simulated is that fuel reacts and retains heat differently than the air. Obviously, it's an oil-based liquid, and it takes time for temperatures to change. Our temperature is actually going up. It's being heated, and most likely what's happening is that in the wing, right, the wing is absorbing sunlight and may be a little bit warmer than ambient. But in any case, if it does, and you may see on very cold mornings, right, if there's fuel left over in the tank, fuel coming from the fuel truck is warm, but if there's fuel in the tank, you may see a fuel low temperature warning. Looking at the pump status here, oh, there goes our AHARS, just aligned. Looking at the pump status, we've got pump B on. There's 3 fuel pumps per tank, A, B, and C, and they're selectable here. So pump A, pump B, pump C. And each flight we change what pump we're using just to kind of spread the load. The logic is also very cool. If you have a fuel pump failure, if you have pump C failure, for example, the system's going to cycle between pump A and pump B till you select one. So 3 redundant pumps per tank. You can see that tank 1 is off, so it indicates an off status, whereas here we don't show an on, we show a B, showing what pump is on. And then you can just see the quantities on the side here. Alright, now that we have fuel, let's go ahead and get the APU started. So, APU here, first thing we want to do is actually test the fire detection system, make sure that before we start anything that burns fuel, make sure that we have the ability to stop it if it starts burning fuel wrong. So the fire detection logic, we have a 1 test button. It tests both each engine fire detection, it tests the bag smoke, it tests the APU fuel shutoff and fire extinguishing, and it'll present a big array of indications on the EICAS here. So let's go ahead and test that. We press and hold for a couple seconds. You can see the warnings pop up. We get a master warning, master caution, and a fire bell. So we got a whole slew of warnings there. We got bag smoke, we got engine 1 and 2 fire, APU fire, we got engine 1 and 2 fire detection fail, and APU fire detection fail. Reason is that when you test it, we send a test signal, but the signal actually, the fire detection fights back. It actually goes, I don't sense that, but I'm getting told that I'm on fire, so it kind of triggers its own self-doubt logic, triggering a fail condition. So that was a successful test, actually, and those are a list of messages you want to look for. We heard the bell, we saw the fire handles both light up, and we got a master warning and a master caution for those sets of warnings that came up. So a lot happens when you test the fire detection. Now, one thing to be careful of is you don't want to test it longer than 10 seconds with the APU running, or it'll actually shut down your APU. It won't dump anything into it, but it does shut down the APU. It triggers a condition that the APU auto shuts down. So that was a good test. I'm happy with that. So let's start the APU. First thing we do is we take the controller and we turn it to on. With both the APU and the engine, something to be careful about is they're both computer controlled, so you have to let the computer warm up and test itself. The APU came alive and we saw that there was a test indication. Let's see if I can do it again here. Yeah, here you go. A flashing box around the APU percentage and dashes for the temperature indicate that it's doing its own self-test as it boots up. So give it a second, let it get through that. Once you have a solid box around the RPM, you're good to start the APU. And what we do with that is we go ahead and we just bump the starter to start and release. And you can see the APU. Temperature climbs. As the APU starts, you can hear the avionics fans cut off. It does take a decent amount of power. It's a starter generator. So often what happens is the avionics fans kick off. If you're starting the APU using just the batteries, it's actually important to disconnect both avionics push buttons. Reason being is it just really helps the system with electrical load. It takes a lot of battery power to start the APU, and so you really don't want to be also powering avionics while you do that. So the APU is stable after 7 seconds above 95%. And now we have an APU. We don't need the ground power anymore, so let's go ahead and come over to our electrical page. We see the APU is alive. We can go ahead and deselect the ground power. So first thing you want to do, always deselect the ground power before you pull the plug. If you pull the plug with the system still looking for it, it causes a lot of problems with this airplane, and the only way to fix it is just like your computer, turn it off and on again. So let's deselect the ground power. You can see APU takes the load. And we get a warning. We get a warning saying the shed bus 1 and 2, so quick crash course on Embraer logic is a dash, 1 dash 2 is 1 and 2. So this is saying shed bus 1 and 2 are off. I brought up those shed buses a few minutes ago. What the shed buses are doing in this case on the ground is they're looking for 3 generator sources. They're looking for a Gen 1, a Gen 1, Gen 3, Gen 2, Gen 4, the APU. It's looking for 3, any combination of 3. Without 3, the shed buses drop off because they basically say, okay, you only have half the power we expect to fly around with. We're going to conserve power and drop the shed buses off. Again, at an engine failure, I'm not worried about powering the coffee pot. Problem, though, is that on the ground, right, sitting here at the gate, we do want the coffee pot. We do want the CD player in the cabin. We do want to be able to have lights and things like that. So we take the shed buses on the ground. If you go to override, the shed buses are enabled with at least 1 generator. So we have 1 generator source. The APU is alive. In override, the shed buses are now enabled. Now watch what happens to the electrical load here. So shed bus is off. We're sitting around 260 amps on the APU. The shed bus on. We come up to, we're cruising around 300. When you first start the aircraft, when it's from cold and dark, a lot of systems take a lot of power to get moving. So when you first start it, you'll actually see that with the shed bus on, you get what's called a gen overload condition, APU gen overload. Any of these generators, all these generators are rated to 400 amps. And if you start going above, if you go above 400, you'll get a gen overload warning you need to reduce load because you're overloading your generator. So that's another use for the shed bus, is that it has the ability when we're starting the airplane. We always start the APU with the shed bus in the auto position when we're starting up the airplane, just to make sure, right, that we have the ability to check the loads before we turn to override, just in case we start overloading our APU. In this case, we're good. We have a nice warmed airplane and things are running well, so we're only drawing 300 amps. Everything's great. APU showing 28 volts, which is its rated voltage. So that's good. We can go ahead. You can see that it's charged our batteries as well. And we can go ahead and go deselect now, because remember, GPU is not being asked for, so be careful, right? We're not asking for it anymore. We can go ahead and deselect our GPU. And the GPU indication goes away. And we're now sitting here on the APU. Alright, finishing up with the APU panel before we move on. A couple other things we have. We have the APU extinguisher, which is selectable. I'm not going to, because I don't really want to dump a bunch of halon into my APU. But selecting this will do a couple things. So if you have a fire detected in your APU, you're going to get that fire bell. You're going to get the APU fire master warning. And you're going to select this and press on the APU extinguisher. It's going to do two things. First thing it does is going to close this APU fuel shutoff valve. We have a manual controller here in case that doesn't happen, but the extinguisher should automatically do that, and that shuts off fuel to the APU. And then it's also going to dump the halon bottle into the APU to try to put out the fire. The fuel shutoff push button here is for if the fuel shutoff valve doesn't close. This is basically the way to hardwire it closed. And then remember that this master controller, think of it, I think of it a little bit more like the FADEC computer controller for the APU. The APU is monitoring itself for a whole bunch of conditions like an overvoltage or an overspeed, things like that, a fire indication. It's going to shut itself down for, there's about 15 things it'll shut itself down for, and then a whole list of things it'll do it in the air. So when we shut it down, we actually press the stop button. We don't want to just turn off this master because that actually tells the FADEC shut off as well. We want the FADEC to monitor the whole shutdown of the APU, and then when the APU, actually I have it up right here, reaches under 5%, you can select it off. But you don't want to do that before that because you're basically turning off the controller with the thing still on. So what we do instead is we press this stop button, and what this stop button does is sends actually an overspeed signal to the APU, tricks it into thinking it's overspeeding. It's just a weird behind-the-scenes thing that's going on in the logic. And that sends the APU, starts spooling down the APU, cuts the fuel off. Once it, like I said, once it reaches below 5%, you can go ahead and select the master off, and the APU will indicate off. Okay, I think that's enough on that panel. Coming down to our ignitions here. So these are the controllers for the ignition to the engine. We have a 3-position off, auto, and on. Off does what it sounds like. No ignition will be sent. No ignition signal will be sent to the FADEC, so the FADEC will not command ignition during a start. It also will not send any fuel. So that is, for example, if you have to motor the engine. I've yet to actually have to do that, but you know, if it's a maintenance procedure or something you need to maybe clearing, for example, if you had a weird start and you need to clear fuel, you may be instructed to motor the engine. So you'd select the ignition off, run the start-stop selector, and the engine will spool to the maximum RPM it can attain using the starter and just hold that for a while, and there's limitations on how long you can do that without adding fuel or a spark. Auto is the mode we use most often. Auto will, there's a logic that says, so we'll do a startup at the end of this video to show you what it looks like with the start, but in auto, when the N2 reaches 28.5, you'll start having fuel flow, and at 14% N2, you'll start having an ignition. You'll see ignition come on, so the ignition comes on at 14%, fuel flow at 28.5, and the engine will run through its start sequence. On cold mornings, so here in Portland right now, we're at minus 10 degrees. It's pretty cold. We would actually position the ignition selector to on. At my company, what we do is if the temperatures are below 5 degrees and the engine has been off for more than 90 minutes, so we call that a cold engine, which, as you can see by our temperatures, is quite true, we will use the ignition to on. And what that does is, first, it just helps to start a little bit more. Each engine has 2 FADECs, A and B, so we have a 1A and B and a 2A and B, and they command their respective ignitions. You can see from the EICAS, this letter here represents which FADEC is active. During an ignition auto start, you only use one channel of the igniter, but during an ignition on start, you use both, and that just kind of gives, reason we're doing this is so that a cold engine has just a little bit more help getting started. We're less likely to get weird start-offs doing that. So let's talk about the FADECs here, and let's talk about our takeoff data. So first is the FADEC. Like I mentioned, there's 2 channels per engine. And what we can do to change them is, and this is something that's not often done at my carrier, we can select a different FADEC using this FADEC alternate. So you can see that I'm switching between A and B right here next to the FADEC, or next to the N1s. Reason we don't do this at my company is that, or it's not often done, is that when you start the engine, once the engine finishes the startup cycle, it swaps to the next FADEC for the next start. So they actually swap on their own, and that gives each FADEC a chance to work at flight. So you'll often see that, you know, one will be on A, one will be on B, because maybe one engine started more than the other, someone taxied out and went back to the gate or something like that. But you do, and some carriers I know do alternate the FADEC after start. It just depends on what your operator does. You don't have to, because again, it's going to just change FADEC when it starts the next time. But you do have the ability as well during some procedures, if for example, a FADEC's misbehaving and something's not working right, you can change to the other FADEC to see if that affects it. Alright, so now on to the takeoff data section. So this is a very important one. You're going to interact with this panel every flight. And what it does is, just like in an FMS on other aircraft where you would set your takeoff temperature, your thrust rating you want, and all other parameters it asks for takeoff, we have to tell the engine, and that's what we're doing in other aircraft as well, we have to tell the engine computer what are the takeoff conditions so that it can compute what thrust it's expecting to put out. So the way that we do that is we interact with this store and this increase decrease button. And let's step through and talk about it. So we press store, and I should bring up the MFD. I press store to start initializing data. And on the MFD here, if you're not on this page, you go to System, Takeoff on either MFD, it doesn't matter which one. This engine page will populate. So normally it starts out blank, and because I've hit store, it populates with some data that it wants us to enter. So the first line is our thrust rating. We have two thrust ratings on this aircraft. We modeled the Embraer 145 with the A1 engines, and it comes with two thrust ratings. It has TO1 and Alt TO1. TO1 is your maximum thrust takeoff. So when you select TO1, you're telling the computer, I want the maximum thrust possible for you to generate under these conditions. And it's not just looking at the engine itself, it's actually looking at the pneumatics panel. So it will kick off the packs when the temperature is above 19 Celsius as well to help generate that maximum thrust. So it has full control over the things that contribute to engine performance. Alt TO1 is your standard D rate. So Alt TO1 is a TO1 10% reduced, so 10% thrust reduction. And this is a mode that we use very often because it saves the engine some wear. And that's obviously good for the engine. Rolls-Royce prefers it because they have to do less maintenance, and so there's a lot of incentives in the real-world flying world to not do a full thrust takeoff. So our company very much encourages us to not do a full thrust takeoff, although there are times where you do one, especially if there's wind shear, or if it's a short runway, or it's contaminated. You often will find yourself having to do a full thrust takeoff, and it's kind of fun. So again, those are the two modes you get. You get TO1, and I'm interacting with this menu using this scroll here, increase and decrease. You get a TO1 and an Alt TO1 takeoff. So you select the one you want. Whichever one you're going to use, you press store, and that moves you to the next line. This line is very important, and this one is a gotcha. If you're used to flying an Airbus, for example, you're thinking about a flex temperature. So temperature, you trick your engines into thinking it's hotter out, and by tricking the FADEC into thinking it's hotter out, the engine produces less thrust, and it's essentially a D rate by tricking your engine into thinking there's more performance, or less performance, I should say. We don't do that in the 145. Reason being is that we already have our D rate mode, either TO1 or Alt TO1. Here we need to tell the FADEC what the temperature is outside. We need to give it something to aim for, because that's its reference temperature. Once it starts, it's constantly comparing its reference temperature to the temperature probes in the engine are registering to determine if things are working properly. So what we do is we match it to outside right now, based on the indications I got here. It's minus 10 degrees, real cold today. So we actually set that temperature. That's the temperature we set. We don't do anything else here. We just set the outside air temperature. And the goal is to try to be within 3 degrees. So obviously, you know, by the time we taxi out, it might warm up a little bit. And as long as you're within 3 degrees, you're in the ballpark. But if it's more than that, you might want to reset your data. And that's all we set there. We don't do anything else. No artificial flex. Then we scroll down to the engine or reference anti-ice line, and what this is looking for is, are we planning on using anti-ice during takeoff? Reason this is important is because anti-ice takes air from the compressor, hot compressed air, and runs it through pneumatics to go to anti-ice surfaces, and it's stealing performance. When you take air out of the compressor, you're stealing air from the engine, which is going to reduce the engine performance a little bit. And we need to tell the FADEC that we're going to do that. If we are, Because you can imagine, right, if the FADEC thinks we're going to make, 92% power, but by stealing that air from the compressor, we can only get to 88, well, now we have a mismatch, and that's going to make the FADEC very angry, and we're not producing the power expected, and problems start occurring when we do that. So instead, what we do is we tell it, hey, expect, and then it's going to do calculations to figure out how much performance loss that anti-ice is going to give it. So one of the conditions that's going to require you to use anti-ice during takeoff, obviously, is taking off during icing conditions. If it's snowing or ice, freezing rain, or any condition, obviously, where you're like, yeah, I'm going to have anti-ice on. The other one is if it is a contaminated runway where the temperatures are below 10 degrees Celsius. So, for example, if you have water on the runway, say it's, just above freezing, so the surface isn't icy, but the water on the ground is, it's just above freezing. Well, your wheels might kick up that spray, and that spray might mist into the engine. And in the engine, the air accelerates as it goes into the engine, and it cools down. So that can actually cause it to go below freezing, and now you're starting to ice up your engine inlets. So whenever it's below 10 degrees and there's water on the surface, or you're in icing conditions, or it's raining, we also run engine anti-ice on. We may not do the wings, but we will do engine. So for that case, for example, right here in Portland, it is snowing. There is snow on the ground. So because we have snow on the ground and we're below 10 degrees, we're actually at minus 10, we'll go ahead and say, yeah, we're going to have engine anti-ice on. So now that I've selected that, my engine takeoff data has been sent to the computer. Now notice nothing changed. It's still in amber. We still have this engine no takeoff data warning. What this is saying is, hey, I don't have takeoff data. I don't have data. It can still start, no problem, but it doesn't have a takeoff target. There's no target on this N1 display for us to try to set. And that's the computer's way of warning us about that. That's totally normal right now, because the way it works is after an engine starts, the computer goes to work. So the computer starts comparing parameters, and after a couple minutes, it's going to return a solution. If the temperature it detects is within limits, and the pressures are right, and the anti-ice solution makes sense to the engine, it's going to go ahead and accept the data. You know the data accepts because of two indications, or I guess three. This will all go blue, meaning it's good. You'll see on top of your N1 here, you'll see the thrust mode, right? You'll see it transition. We don't have a thrust mode right now, but you'll see Alt TO1 or TO1 come up telling you, yep, we took it. That's what we're going to try to make. And engine no takeoff data will go away. So again, not a problem right now, but if you're about to take the runway and you still have engine no takeoff data, it might mean you need to reset your data, resend it, because something didn't like something. All right, moving on, we come down to our start-stop selectors, and these are similar to the APU master in that these are how we interact with the FADEC, what we're asking the engine to do. So obviously, we ask it to stop, we ask it to start, or we ask it to run. So a big gotcha with this, and what they teach us, is that these are a request, but the actual indications on the EICAS are the truth. Reason being is there's one big gotcha in Embraers, and it's a safety feature, but it can bite you. The gotcha is that the thrust levers need to be in idle before you can start or stop the engine. This is a safety feature because you can imagine, right, if you're flying around with your thrust lever up, you do not want, right, any possibility that you can turn up and accidentally or maliciously try to turn this off. If you select stop with the thrust lever not in idle, nothing's going to happen. Engine's going to keep running all day. However, that can pose a problem, and especially with a shutdown. When you're shutting down the engines, let's just say you're taxiing at the gate, maybe you're doing a single engine taxi, and you leave your thrust levers like that, where it might be so close that you almost didn't tell, but they're not in idle, and the computer didn't quite register an idle command. And you go up and you rotate this to stop. Well, nothing's going to happen. Your thrust lever, your engine indications are going to show that you're still running the engine. The engine's going to stay running. So we always make sure that the thrust levers are in idle, and then we also always make sure that our engine indications are actually showing. Remember, this is a request, this is the truth. So a big one to look for is fuel flow, because a shutdown engine is going to have no fuel flow, obviously, because it's not asking for any fuel. But a running engine might, so when you turn those to stop, just make sure, and same when you turn them to start. We'll go over starting the engine in a couple minutes when we do it. But when we start the engine as well, make sure that you're actually showing, N2's actually rotating. Don't be sitting there like an idiot just waiting for the engine to start. Actually verify that your engine, you did send a start command. Alright, continuing through here. Lights are lights, obviously. Go ahead and get these on. The next order of business is the hydraulic panel. So, hydraulics on this aircraft, the way the flight controls work on this aircraft is our ailerons and rudder are hydraulically boosted, and our elevator is completely manual. So, the elevator is actually directly connected, control cables directly from your yoke to your elevator, which is part of the reason why we have a gust lock. We have a gust lock because, again, what works one way works the other. If it's a windy day and you don't have a gust lock, so when your gust lock is inoperative, you have to spend your whole time holding the yoke because it's going to try to move around. Your ailerons and rudder, though, are hydraulically boosted. They are mechanically connected, so you can control this aircraft without any hydraulics. It is very, very difficult. We do it in the simulator, and it actually requires both pilots to roll the airplane, as in both of us have to use our strength to try to roll this airplane. It feels like the yoke's made out of concrete. We have simulated that here, actually. Without any hydraulics, the aileron still works with the gust lock on. This is full yoke deflection on my controls, and you see how it's really sluggish? This is now neutral. That's full right I'm commanding. So we've actually gone ahead and simulated that. We've simulated the heaviness you'll feel. So if you want to give yourself a real challenge, try disconnecting your hydraulics, or I guess try to do simulate a hydraulics failure, and we'll talk about how you can do that. And try to fly it around. It's going to feel really heavy, and we've gone to try to really simulate the fact that obviously I can't make you have to use 200 pounds of force because I don't know what hardware you have, but I can make it feel very, very heavy and sluggish. Our hydraulics panel here, nice thing that they did is they told you everything that's on each hydraulic system. So system 1, got aileron 1, rudder, system 1, spoiler inbound, brake outboard, or spoiler inboard rather, brake outboard, thrust reverser 1, landing gear, nose wheel steering, and the main door. And system 2, same thing, with its brake emergency being the big difference. And some of the things that are here aren't here. So that's really nice. When you have something wrong, you don't have to... Obviously, they're going to tell you that in the manual too, but it's nice to be able to look up and see it. And just like I was talking about with the electrical system, Embraer has given us a diagram. So system 1, system 2. Each system has 2 sources of hydraulic pressure. So let me pull up the hydraulic page here. So the hydraulic page shows brake temperatures, and it shows the hydraulic system, pump status, pressure, and system quantity. System quantity looks good. You always want that in the green. Definitely don't want to see any amber. You don't want dispatch like that. It shows system pressure, and then pump status, so what pump is running. So the 2 sources of hydraulic pressure are the engine pump. The engine has a pump itself, and we have the electrical pump. The engine pump is attached to the engine, and you actually can't disable the engine pump, but what you can do using these is you can shut off the pump hydraulic fluid. So if we have a problem with the engine pump, we can deselect the fluid going to the pump. So basically the pump's still going to spin, but we don't let it have any fluid to actuate. And that's like if your pump, for example, sprung a leak, you don't really want it pumping all your hydraulic fluid overboard. We also have an electric pump. The electric pump is a 3-position switch, off, auto, and on. Auto, the logic basically says, on is we hardwire the pump, we select it on, pump comes on, so we can do that here. And you can actually hear it. And now only system 2 is out, so you can see the message is new, because system 1 is now working. You can hear the whining. You can really hear it in the cabin here if I go to the cabin. It's quite loud. So with on, you can see the indications are electrical pump on, and hydraulic pressure came up to 2,900 psi. So on is simple. That's simply turning the pump on. Auto is a little more complicated. So in auto, the pump is looking at pressure. If the system pressure drops below 1,600 psi, it's going to kick the pump back on. It's going to turn the electric pump on. And it's looking at the entire hydraulic system. So basically, if you lose the engine, one way to think about it is you lose engine 1, right? Well, the engine pump's not giving you anything. The pressure's going to drop off, and if it drops below 1,600, this pump comes on and boosts it back up. So right now the pump's on, and it's boosting the pressure to 29. Why? Because our engine's off, so we have no other source of hydraulic power on System 1. So basically, when you're flying around in flight, you'll actually see your electrical pumps indicating off. Why? Because your engine's running. your engine's running. So there is a source. It's above 2900 psi. So I don't need these pumps. So that's not an abnormal indication. Remember, this just tells you what the pumps are doing. This is a request. This is the truth. So just keep that in mind when you're flying around. If you thumb through the pages, don't think, it's broken. The electrical pump's showing 0 or showing off and cruise. That's normal. If you shut off an engine, or you shut off your engine pump, for example, all of a sudden, now we need the electric pump to come on to keep the pressure up. The engines also put out slightly more pressure. They put out between 3,000 and 3,100 psi. So you often see 3,100 psi indicated. So whereas the electric pump can only put out 2,900. So it's a little restricted on pressure, and it's very restricted on volume. So the engine pump puts out about 10% more fluid than the electrical pump, because the electrical pumps are much smaller and they're running off electricity, so you don't want to make them massive and have them be a huge electrical draw. So now I can go ahead, I can deselect the pump, I don't need it. Pump turns off. You can see the pressure bleeds off towards 0. And of course our favorite warnings come back, because systems have gone, we're dying, because we're sitting here at the gate with engines off. The airplane doesn't know that, so it thinks that it's dying. It's telling us, hey, hydraulic system 1 and 2 have failed. Well, they haven't failed. We just don't have any pressure because we turned the plane off at the gate. That's normal. Oops, it was this one. Moving up. These are how you can also target what you want to send hydraulics to. So in addition to just turning off your pumps and turning off your hydraulics, we do have the ability to say where we want these hydraulics to go. So for example, if you want to isolate the aileron, say you got to get system 1 to not go to the ailerons, you can deselect system 1, and this shuts off hydraulic flow. There's a bunch of valves in the wings and in the stab that will not send fluid to system 1 for the ailerons themselves. And then same with the rudder. The rudder has a 2-system hydraulic. Two systems feed the hydraulics for the rudder. And so, for example, the system 1 is not needed above 130 knots because we have a very, very big segmented rudder. This thing looks like a barn door. And above 130 knots, you really don't want that whole thing swinging as much as you think it does, because you can do some damage or really over-control the airplane. So system 1 should shut off at 130 knots. If it doesn't, the emergency procedure will tell you, hey, deselect system 1. So this is how we have the ability to target a little more where our hydraulics go. Moving on over to our ice protection system. We'll go over this a little more once our engine's started so we can see it start moving. There's 2 different types of ice protection we have on the airplane. We have pneumatic ice protection on the top row and electric ice protection on the bottom. So the electrics, those are a little easier, so we'll start with those, are our windshields and our sensors. So pitot, AOA, pitot 2. These are all electrically heated and have a scheme to them on when they're heated. Remember dark cockpit. Dark cockpit says if it's normal for flight, it's dark. So the sensors are on their own logic. We don't really need to talk to them very often. We don't need to interact with them very often. We can deselect them if there's a failure or something that requires us to reset them. But for the most part, these are kind of dust collector buttons because they live pushed in. They'll come on. These all come on when the engine starts. So when an engine starts, the airplane starts heating up its pitot, its AOA. The only one that doesn't come on, and it heats up its ice protection. The only one that doesn't come on when an engine starts is the total air temperature. That one comes on when you push the power up for takeoff, so that's the only one that's an outlier. The rest all come on with engine start, and they all do this on their own. If they don't, then you're bringing out a book that's going to tell you what to do, and usually it says cycle it, try again, and then, all right, I guess we're pulling over, calling maintenance. The windshields are simple. They do not have any sort of scheme to them. They are simply on-off. So we turn them off at the gate unless we really need them. Just for 2 reasons. One of them is you actually hear them in your headset. It makes a kind of crackling noise, interference. The second is just to avoid overusing them, especially at the gate. I don't particularly care unless, the windshield's fogging up or we're really, really picking up snow and ice and I want to melt them and the wipers aren't getting them. You can turn them on. So for the pneumatic ice protection, I'm going to actually talk about this row and this knob in conjunction with the top row. These are the engine air inlets, wings, and stabilizer. They're all heated with bleed air taken from the compressor, and they're all controlled by the ice detection system. So that's what this knob comes in. This knob here is how the ice detection override is how we interact with the ice protection system. This airplane has automatic anti-icing, so you don't need to turn it, you don't necessarily need to be turning it on and off and on and off like some other aircraft, but you have to understand how the logic works. So in auto mode, that's the default mode for this knob, the ice protection system is controlled by the ice detectors, and there's a scheme they follow. And essentially when they detect ice and the scheme is followed, it will open, and you'll see an open inscription in the anti-ice valves. You'll also see an ice condition EICAS. And that is the airplane saying you're in ice conditions, we've detected ice. Up here is the valve status, so whenever you see that ice condition, which unfortunately I'm not able to replicate at the gate, but if you see the ice condition, you want to look up and make sure these valves say open. Because that tells you, okay, all of these valves have opened, and air is going to where they need to go. If you want to monitor how it's going, you may want to pull up your anti-ice, ECS anti-ice page. Reason being is you can see your bleed temperatures, and your bleed temperatures for anti-ice need to be in the green. Otherwise, you'll get an anti-ice low capacity or a bleed low temperature message. And if that happens, especially in like descents, if you're in a prolonged descent, so you don't have a lot of power in your engines, your bleeds aren't very hot, you may actually need to kick up the power. In fact, anti-ice will actually kick up your power for you somewhat. You may need to kick it up some more. Descending in icing conditions can be really annoying because you're trying to get down, but the power comes up in order to keep the plane anti-ice free. So if you're descending in icing conditions, you need to kind of plan ahead of time and maybe do a shallower descent to descend earlier. We have the engine position. What the engine position does is it always gives you engine anti-ice. So as soon as an engine starts, you'll see the anti-ice, and we'll do that here because I want to show you how it works when we start the engine. But it's basically saying, always give me engine anti-ice. The other two are going to be controlled by the automatic ice detection and the logic protection. Then we have all. All is basically, I'm not asking, I'm telling. And it always gives you engine anti-ice. And then it will give you these two as soon as it can. There is still a protection. What we don't want to do is we don't want to send the wing and the stab. We don't want to send hot air through there unless we have a little bit of airflow over the wings. Reason being is that the engines actually have a lot of airflow. Whenever you heat the leading edge of something, it gets really hot, and airflow is how you remove that heat. Well, obviously the engines are inhaling air very quickly and removing that heat, but the wing and stab, if you're stationary, won't do that. So it's actually inhibited below 25 knots always, all these modes are. In the all mode though, the difference between engine and all, because both engine and all will give you engine anti-ice on the ground, is all always opens everything. So if it can, so above 25 knots, and engine always. So in flight, if you turn this to all, you will get everything. No matter what's going on, as long as you're in flight, turn this to all, everything will open. In engine, you'll always have the engine, but you won't necessarily get these two unless they trigger. So think of it as auto, it'll only go if it triggers. Engine, get the engine, and these if it triggers. And all, above 25 knots, you'll get everything, no matter what's going on. So this is how, like I said, we interact with the anti-ice system. So it's a very important knob. On the ground, right, since we're going to be taxiing around on an icy ramp, we already talked about how we're going to be using engine anti-ice to prevent anything kicked up from getting inhaled into the engine and freezing. So I'll leave this knob here, and when I start the engine, you'll see what happens with the engine anti-ice. The test knob, we do this first flight of the day. There's a test we want to do on the ground before we do anything with pneumatics. Just sitting here at the gate, we can do a test here to make sure that we want to test to make sure the logic controller is working. So what I'm actually going to do, we do this first flight of the day, is we place the override in auto, and we press and hold this test button, and watch what comes up on the EICAS. We get two messages. We got ice detection 1 fail, and we get an ice condition flashing. So that's that ice condition. That's basically, we've tricked the sensor into firing. There's the ice condition. And it's telling us ice detection 1 fail. Why? Because we're sending a test signal and overriding its own logic, so it doesn't like that. We do the same on number 2. And we're making sure that the system logic exists. It works and it woke itself up, right? We want to make sure that the messages are basically saying, hey, you've tricked me, so I don't like that. I'm not detecting ice, and that's a good thing. That to fail. I'm not detecting ice on system 2. What are you talking about? That's actually a good thing. So that's a test we do on the ground, and that's just, we do that first flight of the day, and that just tells the system, or checks the system out, make sure it's working electrically. Alright, speaking of hot air going places, let's talk about the pneumatics panel. So the pneumatics panel, once again, is another diagram-based panel. You can see that we have our bleed sources on the bottom and where the air goes on the top. So we have bleed 1, bleed 2, and the APU bleed. We have a cross bleed knob. What the cross bleed knob does is it controls the flow of air from the left side to the right side. We have 2 pneumatic channels on this aircraft. And then we have our PACS, pressurization control systems. So those are going to convert that bleed air into nice conditioned, breathable, pressurized air for the cabin. And then those go to temperature controllers for the cockpit, for the cabin. And we have a recirculation fan, and we have a gasper. These are the ones above passenger seats, and then this is a recirculation fan. This lets us blend some cabin air that we have back into the system. So essentially this is like that recirculation mode in your car, where if you want to use some of the air that's in the cabin in your air conditioning, then you would select, we use that. Otherwise, if we take it out, we're only ever taking in fresh air. We don't interface with these two too much. The reason you may use the recirc fan is on a really, really cold airplane, or correction, a really, really hot airplane rather. If you turn off the recirc fan, it's only ever going to pump air from the new air from the pack into the airplane, which is kind of good, because when it's really hot, what you don't want to do is start feeding in warm air back into the loop, because that's going to just make it much more difficult to cool the system. Once the temperature reaches a good cabin, or a good point, you can go ahead and turn the recirc fan back on. So let's go ahead and configure for ground operations here. We started our APU a while ago. Let's go ahead and get some air to the airplane. So we have an APU source, we have a bleed source, we have the APU, and remember, it's a dark cockpit, so if you see a light on, that's telling you that's not normal for flight, which makes sense. Our pack should be on for flight if we want to pressurize, and our engines in flight are normally doing the supply. So this is normal here for the ground, but not normal for flight. It's not normal to have the engines not be supplying. It's not normal to have the packs off. That makes sense, but right now what we want is we want to use the APU. So we're going to actually ask the bleeds to stay off. Reason being is in the 145, the APU bleed takes less priority than the engines. The engines have priority over the APU. So if you have an engine bleed selected, even if that engine is off, the APU bleed's going to close. So we don't want that, because then we'll just be using an engine that isn't on to provide air that doesn't exist. So let's go ahead and turn those off, which we've done. And we select the APU. Now notice it's striped. APU bleed is striped because it's actually not normal to fly around with your APU bleed. But it is normal right now on the ground to use your APU bleed. Now nothing's happening. You don't hear anything, you don't see anything, and the reason is because we haven't given the air anywhere to go. So the APU bleed is being asked to open, but it's actually not going to let itself open until we give it a path. So let's go ahead and give it a pack. You can hear the pack come online. I gave it pack 1, which provides the cockpit. And all of a sudden we have an open inscription. That makes sense because now we've given it a way to go. The air's coming in through here, through this branch, and up through the pack. Now if we want to send air to the right side here, we have to open our crossbleed. That just ensures that the air from the APU bleed is going to make it to the right side and up to pack 2. And now I can select pack 2, and air is now flowing off both sides. The crossbleed logic here, we do have an auto, an open, and a close. In open, we hardwired it open, and we do this on the ground just to ensure that air is going where it needs to. Auto mode is where it lives in flight, and for most other operations, you're going to use auto. But auto will not open for simply packs. I guess the aircraft considers that we don't care much about cooling the cabin. I'm not going to automatically open for that, which obviously if you've sat in the cabin on a hot day is very important to you. It will open for things like starting the engine or crossbleed start or anti-ice. So on the ground, we call this configuration 3 white to the right. We got 3 white and switch to the right. And this is very important. This is how the pneumatics panel needs to be set up to start the engines. In addition to providing yourself air conditioning here, you will not be able to start the engines if you don't have it set up this way. So a common error, right, is someone's got the engine bleed selected. Well, look what happened to the APU bleed. It closes. Because we've selected an engine bleed, even though the engine isn't on, the logic doesn't know that. It just knows, hey, you're asking for an engine bleed, I'm closing that APU bleed, and now you have nothing to start the engines with. So just remember, when you go to start the engines, this is how you want things to look. All right, let's look at some of the controls on the main panel here. Start with this new radar. This radar is really cool. It's developed to integrate with the X-Plane 12 radar system, so it works really well natively. And it's all new for this version of the 145. So we have a gain knob, and we have the ability to select when it's pushed in. So this knob is pushed in right now. We have automatic gain. Gain is the sensitivity of the radar. You know, how likely it is or how sensitive it is to returns. For example, so if you pull it out, you're in manual gain, and now we have the ability to rotate this knob. If you're, for example, having a hard time picking something up, say that, you know, you're really not picking up something, you can turn up your sensitivity to really just try to get it. If you want to discern a little more, maybe your whole screen is lighting up and you want to just pick out the big cells, you can turn your gain down or leave it in automatic. We have the ability to control tilt. Again, pushed in is automatic tilt, and what automatic tilt does is it uses the aircraft altitude and pitch, and it uses that to figure out where we need to aim the radar. Remember, radar is three-dimensional, and it's not just useful to have it on, you need to be looking in the right place. The radar sweeps side to side, so we don't know anything about vertical, and you can miss weather. For example, if your radar is looking straight up while you're climbing, you might miss something below you. Or, if you're beginning your descent, for example, you don't want to be looking up at the sky. It's very easy to be painting the wrong thing. Or, for example, if you're low to the ground, you might be picking up just the ground, and everything lights up like you're going to die and fly into a storm when actually you're painting the ground. So tilt is very important. The automatic mode does uses the altitude, like I said, and the aircraft pitch and trajectory to figure out where it wants to aim it. If you pull it out, you can have manual mode. I wish we had this on my, or automatic mode on my fleet. We simply have manual, and so what we usually do is start with the radar aimed about 5 or 6 degrees up, and then bring it down as we climb, and our flight path stops being more vertical and starts becoming more horizontal. The radar control mode, this is how we control the radar, so what mode we want to be in. Off, the radar is completely de-energized. Standby brings it to life, it's in a standby mode. And then weather is our default weather radar mode. There's a mode called React, and this is useful for looking for holes, the sucker holes, where a thunderstorm is so big that it actually absorbs radar returns as opposed to spitting them back, and it starts to make things look like a sucker hole that when actually it's weather that's so big it's absorbing. Ground map it's kind of the poor man's terrain radar. It's essentially a mode designed and calibrated to return the ground. This is useful, for example, if you want to see coastlines. And then flight plan mode lets you, it's not actually a radar mode, it just lets you zoom out the MFD a little farther, see more of your flight plan. Test is going to put your radar into a test mode. So to enable your radar on your MFD, you need to actually select it as a field. So if we return to the main menu, whenever you see this menu, you're in the main menu here. We were in the systems page looking at systems. We can come over to weather terrain. And you have the option of selecting terrain or selecting weather. I clicked it once to select weather. A couple things happen. The first thing, let me deselect it to show you what happens if you don't select it. If you don't select terrain, the only way you have to change your, weather, the only way you have to change your map scale is this ring here, this knob here, which changes your scale. Some people like it. Most people, though, like to use these in and out, which don't work unless you select weather. We have to select weather in order to enable those, and then because we're giving the weather radar panel control. And then if we select standby, for example, now we're in force standby, I can control my range using these knobs, or these buttons, which is pretty nice. So this force standby mode is also important. This is the anti-ground crew microwaving mode. Forced, it's standby, but it's actually being forced. As in, we have weight on wheels, the radar will not let you select a weather mode unless you override the standby, which you don't want to do. So I can even select weather, and it's not going to let me do this, or it's not going to let me select radar because it's not good to have your radar aimed at everybody in the terminal and all the ground crews. And then up top, we have a couple other things. We have sector, which when the radar is active, just changes it from being a wide beam to a narrow beam. So it changes the area it's going to scan. So if you're really fixated on something here, you can select that to have the scan stay within a smaller area so you get more up-to-date info as opposed to waiting for a full scan. Stab stabilizes the radar, so, or disables stabilization rather. The radar is stabilized so that when you select, the angles are in reference to the horizon. So when you see something saying 3A, right now we have 3 up, 3 above. That's in reference to the horizon, not to the aircraft. So you can disable that, and basically it's like a bore sight mode where now it's slave to the nose. I've never used that. I'm sure there's a point where that will be useful. Turbulence detection, we don't have that on my fleet, so I can't speak too much to it, but it is designed to, I guess, find and return areas of turbulence, which would be nice to have, but yeah, we don't have that on my fleet. So one of the new highlights of this version of the ERJs is the new FMS, faithful to a Honeywell design. So those of you that have experience with Honeywell, or those of you that fly the 145 with Honeywell equipped FMSs, you're going to be at home here. We're not going to do an FMS video because we will be doing a demo flight later on, and that will show more about how to use this. But just to show you, it's a very capable FMS. It's very similar to the one in the Citation. And it is, if you're used to flying the E-Jets, you're going to find it similar. Remember that everything in the 145 evolved into the E-Jets, so think of the E-Jets as an evolution. So you'll see stuff that feels the same, but is usually more refined in the E-Jets because, again, they're about 10 years later in design. And like I said, I'm not going to go through programming the FMS because the purpose of this video is to show systems and do an engine start, but definitely a very, very exciting feature that we have here, very capable program. One of the newer stars of the show, and something very cool that we have now, is the Gust Lock. So like I said, the aircraft has unpowered pitch controls. Elevator control is completely unpowered, and it is directly connected to the tail via cables and pulleys. So on the ground, we have to lock the elevator in order to make sure that it doesn't flap around in the wind, incur damage, and smack you in the knees, and all sorts of stuff. The ailerons are free, so they can move, but remember with the hydraulics off, they're very heavy. To release the Gust Lock, we also have included an automatic mode. One of the new settings is an automated Gust Lock. So with the automated Gust Lock, you can release it in one click and have it completely go through its release sequence and release the Gust Lock. I prefer to do it the manual way just to show you how that works. With the Gust Lock, there's a 2 position. So the first position unlocks the elevator, and the second position completely releases and allows full travel of the throttles. So to unlock the Gust Lock, first thing I want to do is I want to slide it to the intermediate position, and you can see this Gust Lock illuminated here. It takes about 10 seconds for the pins to fully release. Once released, you can pull the yoke all the way back. And then with the yoke all the way back, slide the Gust Lock to the forward position and release. Now what you want to do is complete control, check, verify that it is actually released. You do not want to take off with the Gust Lock on. I imagine that's quite bad. And now your Gust Lock is free and your throttles are able to move to the full range. I'll try to set it with the Gust, I'll set power with the Gust Lock on in a sec, and you can see what happens when you try to push above. To lock the Gust Lock, we take the yoke all the way back, slide the Gust Lock all the way back to the rear position, and then push and hold it forward. The yoke gets stored in the forward position, nose down. And so now I can release pressure on the yoke, and the yoke is now locked. All right. And actually, I should have done this with the Gust Lock release, so we'll go ahead and do one more for your viewing pleasure. Last thing, or one of the last few things I want to highlight here before we go ahead and get this thing turned off is the new stall protection system. So once again, I'll pull the stick all the way back, release it, Gust Lock's free. So with the new stick pusher and stick shaker, we have simulated the stick pusher in the 145 and the stall alarm. And we test, before every flight, we test the stick pusher, make sure that it works. And that's done by holding the yoke back, releasing the Gust Lock, and moving this to the full yoke, full aft position. And you can see that we got the alarm, and the pusher went forward to break the stall before giving me my yoke back. So that's a cool new feature. Hopefully you don't experience that firing on you. That would be bad. But it's cool to test, and it's actually one of the required pre-flight tests. So go ahead and lock that. Last new thing down here is the pressurization controller has been completely done. So the way that pressurization is controlled on this aircraft is we have two systems. We have the automatic system and the manual system. The automatic system, to be in automatic, which is where we are 99.999% of the time, we take this controller, this knob here. This actually controls the outflow valve position. If you turn it all the way counterclockwise to the green, and press it into the green detent, we're in the automatic mode. So this is an automatically controlled pressurization system now. We can use this to set our landing field elevation. So set your destination elevation so that the pressurization system follows a special scheme and it knows what it's aiming for on descent. If you want to be in manual, good luck. No. You take it out of the detent, and now you have full control over your outflow valves, and basically, essentially, 11 o'clock is considered closed, and then, or no rate change, and then now we're commanding rate changes with this knob, all the way from 2,500 feet per minute up down to 2,000 feet per minute down. In the automatic mode, you also have the ability to use the dump button, and that will dump the cabin to an altitude of 14,000 feet. This doesn't work in the manual mode, so if you select manual, right, and you're using this guy, you're going to have to dump the cabin by doing that. Alright, before we close out this video, last thing I wanted to show you was an engine start, just so you can see some of the indications that come to life when you start an engine. Before we do this, we just make sure our thrust levers are idle, our fuel pump's on, our ignitions are going to be selected on to help with the start on a cold engine. Ice detection is set to engine, because remember that there's snow outside and it's below 10 degrees, so we want to just protect our engine inlets from any icing. The icing valves are closed. We'll check back with these after we start the engine. And last thing is that our pneumatics panel APU bleed is providing air. Engine 1 and 2 bleeds are closed, so that's correct. We're going to use the APU to start the engines. Starting the engine, go ahead and take your start-stop selector, place it to run. And one thing I want you to watch on the start is the ITT limit will drop. Right now it's in a takeoff mode, so it thinks that the takeoff limits for the ITT apply, but actually the starting limits are 800, so it'll drop down to reflect that once you bump it to start. Alright, let's go ahead and do it. So there's start. See the limits came down. N2's rotating. Ignition's alive. 28.5%. We're looking for fuel flow. The plane beeps at you, obviously. Alright, there's fuel flow. N1's coming alive. This is a fun little tidbit here. So sometimes starting things, especially the APU, the electrical load knocked the AC bus off, and that's not uncommon. Buses shed, bump on and offline, depending on what's happening when you change generator source. This plane is very electrically fragile, is a good way to put it. Alright, there's a good start. So looking at our after start indications, we have about 25% N1, which is a good idle N1. Our N2's hanging out about 65, which is good idle N2, and our fuel flow is stable, ITT is stable. Oil pressure looks good, oil temperature is coming up. And we have the ignition still on. We don't want this anymore. Now that we started the engine, we can take the ignition and go to auto because it's self-sustaining. It doesn't need help. No more spark is required. And that's a good start on engine 1. Now notice our takeoff data still hasn't been taken. It's still not accepted, it's still not matching what we've asked for. Let's go ahead and start the second engine, and that'll get both FADECs understanding. Before I do that, notice that engine 1 has opened its engine air inlet valve. So because the valves are controlled by engine air, they're operated by engine air, we need the engine actually be running before the valve opens. So that's an open inscription on engine 1. We'll go ahead and start engine 2, same procedure. Pause. Pump it to start. Pressure and N2 are coming up. Ignition. Alright, there's fuel flow. Alright, and the start is stable. Oil's real cold. It's real cold here today. So once again, ignition can come off. Both engine anti-ice valves are open. So showing you that they're both open and commanded open. Close the guards. And let's take a look at some of the things that changed here. The first one is, whoops, our takeoff data went blue. So it was accepted by the system. The second engine started, both FADECs agreed. Takeoff data went blue. We're commanding Alt TO1. I put the wrong temperature in. Should be -10. So, actually, great example here. I deselected, I killed the data by pressing store again, I restarted it, and now I've got an engine no takeoff data, and I have no data markers. A second ago I had Alt TO1 and data markers. Remember, this engine now doesn't know what its targets are. So let's do that again. Alt TO1, engine ice on, it's accepted and the markers came back. So notice how you can also clear your data by restarting it here, and you want to make sure you finish the process. A common thing you might see is, you know, someone gets this far and then they don't press the last button, right? Just make sure that it all goes in. The data's good, it's accepted. Crossbleed's open. That's still open because we're still using APU air. We haven't changed our pneumatic setup at all. We still have to do some work here. And our hydraulic pump is selected off. Notice that all of the hydraulic warnings are gone because we have an engine started. Our engine started, and therefore the engine-driven pump is taking all the hydraulic pressure, pumping all the hydraulic pressure. So system 1 and 2 are happy. All the things are happy, but it's just warning you, these advisory message, hey, your hydraulic pump is not selected to auto. You're not in the state that it should be for flight. So let's go ahead and do that. Message goes away. Plane is happy. And then let's reconfigure our pneumatics panel. Now we no longer need APU air. APU is no longer needed. So we'll go ahead and deselect the APU bleed and select the engine bleeds. And then we can go ahead and take the cross bleed, put it to auto, and now it's gone. Its logic is now being controlled by whatever the cross bleed logic, so if it needed to do something to open, it will open. And the last message here is check A1 perf. This is one of my favorites. It's another kind of idiot detector message. What it's actually telling you, the message is not actually very well written. It's not really accurate, or it's not very clear what it's saying, but what it's actually checking is it's saying, okay, takeoff data was accepted. I have takeoff data. I seem to have a brake set, and I don't seem to have a flaps. The computer doesn't quite register takeoff conditions, which the brake would be off, and the flaps would be set. So it's not quite a takeoff config warning. We still have
no
takeoff config, which checks flaps, spoilers, trim, and brake. So we still have that. That's our failsafe. If we push this power up and we get that ding ding ding, that's actually our takeoff config. But this is sort of a mini takeoff config is how I think about it. To make it happy, we'll go ahead, release the parking brake, and I'll go ahead and set flaps. And now it's gone. Flaps are set to 9. it's now happy. And it now is back because I've set the parking brake. So basically it's looking for the brakes and it's looking for those flaps. It's basically saying, hey, the performance, this isn't the performance I'm thinking I'm going to have. So it's a fun little message that you got right here. Last couple things to show are the electrical system here. So if we look at the electrical schematic, remember how I said the shed buses need to be overridden on the ground unless you have 3 generators. Well, look how many we have now. We have 1, 2, 3, 4, 5. 5 generators. So the last thing we do is we take our shed buses and go to auto. We don't need those. And we can go ahead and shut down our APU. We always turn off the bleeds to the APU before we shut it down. It's better for the APU if you power it down without it having any load. So it's not taking any electrical load and it's not taking any pneumatic load. Remember, we shut it down using the stop button. So I press the stop button and it starts its shutdown logic. At 5% or less, I can turn the APU controller to off. So we just wait for that. Let's see here. While that's going, I can also talk about the bleed temps. You can see that this is showing the temperature in the bleed ducts for 1 and 2. And there's 4%. Go off. The APU powers itself down. The FADEC can power itself down. You wait forever. 1% hangs out for a very long time. This is true in the actual airplane. There we go. And yes, it can take that long sometimes. APU is off, which means the control is turned off, it's closed its respective shutoff valves, and it's now happy and put itself to bed. So that's all for this video. I really hope you guys are getting excited for this plane. I've been flying it around a lot and I really do like it. It's a very, very cool add-on. And it's also just, like I said, the whole purpose of this video is we're really excited to show some of the systems depth. We really pushed ourselves to try to understand and present the messages, the indications, the controls, the things that you'll see. Because it's just cool to see these messages pop up like check A1 perf and, you know, look at that and oh, well, that's because the plane thinks I'm going to try to take off the brake set. You know, stuff like that. They're the cool little Embraerisms that make this jet so much fun to fly. Hope you really enjoy it, and pretty soon we'll be doing the tutorial series on how to actually fly it, and very excited to be doing that, because then we'll take this airplane, we'll take it airborne, and we'll actually take it through a flight and show you all the things that you're looking for on the line. Till then, stay excited.